Interconnecting remote data centers has always been a challenge for network engineers. And since we're dealing with moving both data and virtual servers, multiple methods are required to accomplish this task. The first engineering hurdle to leap is how to connect data centers at the transport level. And we have technologies like dark fiber, vanilla IP, and MPLS, of course, each with their own pros and cons for the data center. Now that we have the transport built, we have to decide how to reliably get the data between sites. Multiple methods, many opinions, all valid perhaps, but instead of trying to manage a bunch of trade-offs and compromises, how about a solution that takes the best of all worlds and puts it right in the palm of your hand? Overlay Transport Virtualization, or OTV, is basically a layer 2 extension that works across any transport for data center interconnectivity. Connecting data centers is not new, but in developing OTV, we wanted to improve on 3 critical areas. First one, going from data plane learning to control plane learning. Number 2, going from pseudo wires and tunneling to dynamic encapsulation. And third, going from complex multi-homing to a built-in, much easier multi-homing. Now let's take a look at the first one, moving to control plane learning. Now in essence, this means MAC address routing. All right, now, I know it sounds a little different, but stay with me here. We are not building out a large layer 2 broadcast domain and undoing all of your hard work you've done to get to layer 3 network. Rest easy. OTV is actually encapsulating the source and destination MAC address into an IP packet. This allows OTV to be core and transport agnostic. As long as it supports IP, OTV will work. Now, not just any encapsulation is going to do here, right? OTV uses Ethernet over GRE. Then, we add an OTV shim to the header. Now, this is basically the 802.1q header copied into the OTV header to encode the VLAN information. The overhead on this process is 42 bytes. Much less than any other encapsulation process. All right, let's get some of the common OTV terms defined. An edge device connects a site to the WAN or MAN. The edge device is the workhorse of the solution since it's responsible for performing all OTV functions. Now, in most designs, the edge device is at the aggregation layer with the possibility of multiple edge devices in a single site. Internal interfaces are interfaces on the edge device that only the internal site uses. These act just like normal layer 2 interfaces, participating in processing spanning tree BPDUs. The external interface is typically a point-to-point routed interface on the edge device that connects the site to the core. Now, for all of you packet tracers out there, the external interface is the one OTV uses to join multicast groups in the core, and it's also the source address for OTV encapsulation. Now, finally, an overlay interface is a virtual interface. It is literally the secret sauce to making OTV work. Multiple sites join each other via the virtual interface. And this is where your OTV configuration is applied and it does not participate in spanning tree protocol. Now that we have some OTV terms down, let's look at how our MAC addresses are learned. Any first-year networker knows that MACs are learned via flooding. Well, this is okay for a LAN, not acceptable in a multi-site data center design. OTV does not flood MACs or STP BPDUs. Instead, OTV devices form adjacencies with each other. They advertise their reachability amongst themselves, and the MAC routing table is built per edge device. Now, this is a dynamic process, and the engineer does not need to configure anything for this to happen. Every time an edge device learns a new MAC address, OTV will advertise with its VLAN ID and next hop IP. Now, let's put it all together and see how it works as a solution in your data center. There are 2 ways to deploy OTV, multicast and unicast. We're going to focus on a multicast deployment. The first step is for our OTV edge devices to find each other via neighbor discovery and form adjacencies. Each edge device joins a multicast group in the core as a host. Edge device A will send a hello, encapsulate it in IP, and send it on to the core. The core replicates the packets and forwards it to the other edge devices where they will unwrap it. Edge devices B and C encapsulate a hello response in IP back to edge device A. Adjacencies are now formed between edge devices, and we've created an OTV control plane. Now, we can start to exchange MAC reachability information. Now, it's important to note that edge devices will join multicast group as hosts and not as routers. This method means that we can add other sites without having to reconfigure the entire OTV grid. Just add the site and join the group, and no additional configuration is required on the peers. Now, to achieve this type of scalability, OTV uses 2 multicast groups for communication. The ASM BIDR group is used to establish adjacencies and MAC reachability information. The SSM group is used for multicast data generated per site. Now, one of the questions we hear a lot on OTV is how unknown unicast packets are handled. Well, the answer? On the internal interfaces, the packets follow the normal flood and learn process since it's a traditional Layer 2 interface. The edge devices will not allow an unknown unicast out onto the OTV grid. However, we still need to take care of our unidirectional hosts. So to solve that, we snoop the ARP reply, learn the MAC address, and add it to the OTV MAC table, and the frame is never flooded. Edge devices handle all ARP traffic for hosts across sites. OTV has a proxy ARP feature to dramatically reduce the ARP traffic on the OTV grid. Now the final piece of the puzzle is how OTV handles multi-homing. Remember that OTV does not forward STP BPDUs. Each site runs their own STP domain. OTV provides a loop-free multi-home design by designating a forwarding device per site for each VLAN. This is known as the Authoritative Edge Device, or AED. The AED is the only device that can forward multicast or broadcast traffic across the overlay. When a broadcast is received at the site's AED forwards it to the OTV overlay, where it's received by all devices. The AEDs at the other sites forward the frame into the site, while the non-AED edge devices, the non-authority ones, drop the frame. All right, let's take a look at what really puts the icing on the cake for OTV, and its simple configuration. You can set up an OTV with 5 commands. Plus, this configuration never needs modifying as you add more sites. How nice is that? OTV was designed from the ground up to give data center architects a new way to look at data center interconnectivity without the complexity or sacrificing of any of the high-end features required for today's data center. For more information on OTV and other data center interconnect technologies, just go to cisco.com/go/DCI.